Okay, then I have to share my screen. Okay. All right. Uh, Let me just sort of a little bit review what we have done. We have learned last week. Okay, the first we learned two models. One is called distributed lag model, and in this model, we found that the lag independent variable appears on the right-hand side of the equation, such as equation 12.1 and 12.2. And the 12.2 is the general form with P lags. Okay, and the problems with distributed lag model
Professor,
is
excuse
the
me.
first one. Yes.
Can you make your PowerPoint bigger?
Yeah. Okay. All right.
Thank you.
Okay. Thank you. Thank you. Thank you for telling me. Okay. Um, there's three problems with this distributed lag model. Uh, the first one is the multicollinearity problem. Okay, and because of the multicollinearity problems, there's no guarantee that the estimated betas will be follow smoothly declining pattern as the theory expected. Okay, the third one is the decrease of freedom tend to increase from two sides. Okay, the first one is if the lag of the x increase, then the coefficient, the more the coefficient to be estimated. The second one is if we do have lag x, it will decrease the sample size by 1. Okay, 1 lag, and the sample size will decrease by 1. Okay, so with these two side of uh, uh, these two reasons, therefore the degrees of freedom decrease. But when we say the problem, it doesn't mean that this model is not is useless. Okay, all right. And the second one, we are introduced the dynamic model. Okay, the dynamic model is the one which we have lagged dependent verb. Okay, and such as equation 12.3. Okay, and remember that the dynamic model can be expressed as a distributed lag model, okay, which is like this way, okay, and the dynamic model with the beta 0 as the coefficient of xt, and lambda is the lag, the first lag of dependent variable. Then if we extended this one as a distributed lag model, there's a relationship between the coefficient with the lambda and beta 0. So for example, with the first leg of x, the beta 1 is equal to lambda times beta 0. And the beta 2 is equal to the lambda square times beta 0. And up to the pth lag, the beta p equal to lambda to the pth power times beta 0. Then we say that as long as the lambda, the range of the lambda between 0 and 1, the coefficient smoothly decline. Okay, so I'm going to continue this topic. Okay, there's a little bit I haven't finished yet last time. Okay, remember that the dynamic model. Okay, let's go back here. The dynamic model was beta 0 and lambda. Okay, this is which means that the long run multiplier implied. The long run multiplier implied in this model. So let's see how does that work. And we know that the long run multiplier measures the total impact of the changes in the x variable to the y. Oh, okay. And if we wanted to, and since we know that dynamic model can be expressed as the distributed lag model, means that when we say the long run multiplier means the sum of all this coefficient, the sum of all this coefficient. Okay, and since we're using the examples last time that we estimated a dynamic model using the consumption as y variables and the income as an x variable. Okay, so beta 0 is 0.46 and lambda is equal to 0.56. All right, so if we express this, in theory, if we express this dynamic model into the distributed lag model, we will have all this beta coefficient. Okay, for example, in this example, we have three lags. So this is beta 0, and this is beta 0 times lambda, and this is beta 0 times lambda squared, and beta 0 times lambda third, the third power. Okay, so if we want to know the long run multiplier measures in terms of just three lags, we can add all this coefficient, sum them up. Okay, but usually when we say the long run means these lags tend to be infinitive. Okay, in this case, okay, I like ask you, all of you, to turn to the page of 388 in our textbook. Okay, there's no PowerPoint here. Okay, if you turn to the page of 388, at the lower part of this page, okay, it mentions about this long run multiplier. Okay, and let me show you how I did it. Okay, so I need to switch to how to switch it this way. How can I switch this back? Okay, all right, let me show you. Okay, I just say that one way to get this estimate would be add up all these betas. In other words, from beta 0 hat up to infinity. But it's troublesome to add them together one by one. Therefore, an easier alternative is to calculate these formulas. So how do we get these formulas? Okay, I just use some of the footnotes here. If I want to add this coefficient together from beta 0 hat until infinity, and in fact, this equation is equal to, on the right-hand side, the left-hand side is equal to on the right-hand side, right? And as we know that on the right-hand side, this is what we call geometric series. With a geometric series, the sum to infinity can be shown is using the first value, beta 0, times 1 over 1 minus lambda. Lambda is the common factor. Okay, I think this is by, you can prove it in math. Okay, but here we're not going to prove it. We just use the result. And remember, this is because this is a geometric series. Okay, there's a formula to use to sum the beginning to the infinity. Okay, so the sum to infinity of geometric series can be shown to have these formulas. And remember that beta 0 is 0.46 and lambda is 0.56. So you just plug all these numbers in and we'll get this number is 1.05. This is what we call long run multiplier, and which all this, in order to get this 1.05, these numbers all embedded, okay, in the estimation of equation 12.11, this dynamic model. Okay? Any questions so far? So I think this is the 12.1 and 12.2 section of this chapter. And the main point is we introduce two models. One is dynamic model. The other one is distributed lag model. And we have to also remember that the dynamic model will overcome some of the problems which we just show in the dynamic model, in the distributed lag model. Okay, the first one is with dynamic model, we don't have multicollinearity problem. We don't have severe multicollinearity problem. Okay, and since there's no multicollinearity problems, then we don't have this. We can extend it to the distributed lag model with the theory's expectation that all the estimated coefficient will follow the smoothly declining pattern. Okay, and then number 3 is the degrees of freedom, will not decrease because we don't have the lag of x variables anymore. Okay, but there's one big problems in dynamic model is what we call zero correlation. We don't mean that distributed lag model doesn't have zero correlations. It may have zero correlation problems, which we talk about in chapter 9. Okay, but the dynamic model is easier to have zero correlations. Let's see what's the reason. Okay, all right, and this is we need to talk about in the section 12.3. Okay, which is on chapter page 389. Okay, this is about zero correlation and the dynamic model. Okay, All right, let's see. Why didn't we say, okay, let me put this way, okay. Uh, let's follow this PPT, okay. As we talked in chapter 9, the serial correlation is more likely to have internal symptoms, right? So it affects the estimated equation in a way that is not easily observable from the examination of just the result themselves. Therefore, the consequences of the serial correlation depends crucially on the type of the model we are talking about. So if the serial correlation is in distributed lag model, then we will have the consequences. It's already outlined in the section 9.3. In other words, there's a 3 consequences. One is the OLS no longer is a minimum variance unbiased estimator. Okay. The second one, the standard error of the beta hat is biased. Okay. But however, the estimation of OLS betas themselves is unbiased. Okay, I think you can also review chapter 9 about the serial correlation consequences. Okay, but if it happens in the dynamic model, then serial correlation causes bias. In other words, the serial correlation in the dynamic model is more serious. And to see how the dynamic model occurs serial correlation problems often. Okay, let's see. If you see 12.3, this is the dynamic model. Okay, remember, if the UT, I mean here, okay, if UT, this is error term, is the follows classical assumption, then there's no problem with serial correlation. But if this one, usually this is not the case. Okay, why? Let's see, if we say that if UT has a serial correlation, okay, so for example, let's see, that's the first order serial correlation. Okay, so remember this one, UT is equal to the row UT minus 1 plus the other error terms. So UT, since UT is equal to this, right? So go back to our dynamic model. UT here is also include UT minus 1. Okay, so the serial correlation, if 12.3 has serial correlation, just like there's omitted variable UT minus 1 in 12.3. You know, this one is equal to this. Therefore, there's a UT minus 1 in here. And we know that before, we know that if we have the omitted variables, then of course it will cause bias. And remember that, look at it, 12.15. Okay, if we lagged one time period, then the 12.3 turned out to be this. In other words, UT minus 1 always has a relationship with YT minus 1. Okay, then remember this one, 12.3, this UT minus 1 is the omitted variables. And since this one is correlated with YT minus 1, therefore, although we didn't see from the expression, then in fact, ut minus 1 will affect yt minus 1. So ut minus 1 is in the arrow terms, and yt minus 1 is in x variables. And ut minus 1 and yt minus 1 has a relationship. Therefore, yt minus 1 is not independent with ut here. Okay? You understand what I'm trying to say? It means that yt minus 1, in fact, we say that there's independent, there's relationship, there's a covariance between yt minus 1 and ut minus 1. We shouldn't have any relationship with the arrow terms with the independent variables. But in fact, if this is dynamic models with zero correlation, and the yt minus 1 definitely has a relationship with ut minus 1. And this ut minus 1 is embedded in this arrow terms. Okay, so if the dynamic models, if we have zero correlation dynamic models, then what do we do? Okay, so the first things is we need to, the first one is we need to test whether we do have zero correlation in these dynamic models. Okay, so if we want to test the zero correlation in dynamic models, okay, what kind of test we can do? We learned in chapter 9, there's two ways, right? One is called Durbin-Watson test. The other one is called a multiplier, Lagrange multiplier test. Oh, remember that? So I like to ask all of you that if the dynamic models, which test we can use? Anybody? You all remember that what's the criteria to use Durbin-Watson test? There are three criteria, right? If you a little bit forgot it, then why don't you put it back to on our textbook, page 302. The three assumptions should be met in order to use Durbin-Watson test. Okay? And the first one is the model includes an intercept. So there's no problem with the dynamic models. We do have intercept. The second one is zero correlation is first order in nature. So we wanted to, so this zero correlation must be first order. The third one is the regression model does not include a lag dependent variable. I think this is the most severe assumption we didn't, most of the, is the most severe assumption that we didn't met. Okay, with dynamic models, because the dynamic model usually always has the lagged dependent variable. Therefore, in order to test the zero correlation in the dynamic model, Durbin-Watson's test cannot be used. So there's only Lagrange multiplier has to use. Okay, all right. So this is what I just say. Since the zero correlation causes bias in dynamic models, it is important to test for it. And unfortunately, Durbin-Watson test is not valid because of the lagged independent variables, lagged dependent variables as an independent variable. Okay, so we need to use the Lagrange multiplier test. Okay, then I think we're going to use the example. We're going to use the examples we just showed last week about this consumption and the income. But before we're doing that, there's some procedures about test serial correlation in dynamic models. Okay, the first one is we get the residuals from estimated equation. Okay, then we will set up an auxiliary equation, which is using the residual from 12.17 as a y, and all of the x variables and x, then plus one lag of the residual as the third x variables. Okay, to test for the first order serial correlation. Okay, then use OLS to estimate this auxiliary equation and test the null hypothesis that this A3 is equal to 0. Okay, and this is the chi-square distribution. Okay, we don't have to do it by hands one by one. We can just use EBUS to do it. All right, so let me show you how to do it. Right. Excuse me. So the data we just use it is macro 14, right? Okay, and with the dynamic models, we just run it. Okay, I'm using what I have already run it. Okay, I want to test whether this model, this dynamic model, has zero correlations. So is that, can you see that clearly? Okay, with this models, okay, then I can use the residual diagnostic and serial correlations, LM test. Okay, then we're going to using the lag is 1. All right, so we need to see this observation times R squared is 10.32. Okay, this is what we call the Lagrange multiplier statistics. Okay, so according to these numbers, and this is chi-square distribution with 1 degrees of freedom, and the probability is 0.0013, which is far less than alpha, for example, 5%. Okay, so this Lagrange multiplier test showed us that the dynamic model, we just have it, do have zero correlation problems. All right. Okay, if you go back to see the explanation in our textbook, which is on page 391. Okay, you may see some of those expressions. Okay, if you turn to the page of 391. Okay, and they also mention the same expressions and the same test we just did it. But the expression they mentioned for the numbers is a little bit different from what we have here. Okay, and this is because on our textbook they are using the program is Stella. Okay, they're using program Stella. Okay, which is different. We're using eViews. Okay, so this number is a little bit different. However, the result is exactly the same. But if we use it using Grados, okay, I think we would have exactly the same result. But we have it. Okay, let me do the Grados. Okay, the CO, right? And we have the YD. I'm sorry. We have the YD. Okay, then we also have the the lag. Okay, which is 1. Let me, this is 1. So, okay, all right. I wanted to have the lag of, this is lag of dependent variable, 1 to 1. Okay. Okay. All right. Let me put this one upward. Okay. So this is the dynamic models. Okay. With beta 0, 0.46 and alpha 0.56. Okay. And now I need to do the LM test. Oh, I'm sorry. Analysis. Autocorrelations. Okay. Then lag is 1. So you see that the result, I just have it. Okay, this is, you see the middle part of this one, this is exactly as what I have from the Grados. From the, let me see, this one. Okay, this is the eViews. Okay, I do have this Lagrange multiplier statistics 10.32 from eViews. And also we have this one from Grados 10.32, exactly the same. Okay, the probability is the same. So the packages using eViews and Grados, they do have the same result. Okay, although using Stella, there's a little bit difference, and you know, there's no problem with it. Okay, all right. So I just showed that how to do the test of the zero correlations with dynamic models. Okay, now I need to do that. Following is to correct the zero correlations dynamic models. Okay, how to correct this one? All right, and all this correction described in our textbook from 391 up to 392. Okay, basically, there's 2 ways. Okay, let me show. Maybe there's a PowerPoint. Okay, there's corrections. Okay, if the Lagrange multiplier test finds the zero correlation, first consider the possibility of impure zero correlation. of course, go back to the zero correlations topic. We always we always to make sure that this is a pure serial correlations instead of impure serial correlations. Okay, we know that impure serial correlations is caused by the incorrect functional form, or the model is omitted variable, something like that. In other words, is the misspecification problems. So if it is pure, then theoretically preferred solutions is to transform the equation similar to generalized least square. So remember, we learned in chapter 9 that there are two ways to solve the problems for zero correlation. The first one is generalized least square. Okay, the other one is using the Newey West corrections. Okay, so here the author mentioned that theoretically the preferred solution is to transform the equation similar to generalized least squares. But for practical purpose, okay, so the author mentioned that unfortunately the iterative nonlinear estimation of the transform equation is well beyond the scope of the text. It means that we also can use the generalized least squares, but all this iterative nonlinear estimation of this transform equation, is pretty hard. But as long as we use the eViews, the packages to do it, I don't think we have any problems. Okay, but the authors, really thinks that in practical purpose, if you use generalized least square methods, it's hard to explain it. Okay, so the author suggests two alternatives. Okay, these two alternatives, it really depends on the underlying theory of the model and the sample size. Okay, so let's see how does the author recommend. Okay, for the alternative one, the author says that if the theory suggests only a few lags values of x, then estimate a distributed lag model. So this is the first alternative. Means that if we already have the theory and suggest that only a few lagged values of x, then it's better to just estimate a distributed lag model. Okay, why it is that way? And because they think most of the econometricians would prefer to deal with the consequences of multicollinearity than face the bias. I will say it again. Most econometricians would prefer to deal with the consequences of multicollinearity than to face the bias. Okay, so if we can use the if the theory just suggests a few lags, then we just use distributed lag model, although we have the multicollinearity problems. Okay, and the second advantage of the alternative one is that the author mentions that all this lag x variables is acting as the proxies for yt minus 1. Okay? All these x lags variables are acting as the proxy for yt minus 1. And such proxies are similar to instrumental variables, and they are especially useful because they are uncorrelated with the error terms. Okay, so this is the first alternative. And the second alternative is that if the sample is small, if your data is really small, the data set is really small. So in small samples, the best approach may be use OLS in the face of zero correlation for dynamic model. Okay, and what's the advantage for this alternative? Because actually OLS outperforms more sophisticated techniques. OS is, everybody knows, is very general. Okay, so actually outperforms more sophisticated techniques. And one reason in the small samples, the estimation of the bias in lambda, okay, will be canceled out if we use the OLS methods. So therefore, the OLS can do better than a technique that eliminates only the bias caused by the zero correlations. And the second reason is that from the evidence, they're using Monte Carlo studies. That the size of the bias introduced by zero correlation in small samples is often very small, very low. Therefore, we can use OLS estimation. Okay, so there's a expression on our textbook on page 392 in the third paragraph. Okay, before 12.4, section of 12.4, the last paragraph, the third paragraph. Okay, so in sum, if the theory calls for very few lags of x's, then we suggest using the alternative one, means using distributed lag approach. And the second one, if the sample is small, we think continuing using the OLS estimation, even in the face of zero correlation, presents the best alternative. Okay, number three, if both the sample and meaningful number of lag axes are large, then we would recommend using distributed lag because of the benefits of instrumental variable approach. In other words, the author emphasized that with zero correlation problem in dynamic models, just use distributed lag models. Okay, and also if the sample size is small, and using the OLS to estimate that, just then it will make the problem just easy. Okay, so far. Any questions? Any questions?
No problem.
You understand what what I'm trying to say?
No question.
Okay, by the way,
Usually, Prof. Usually, for dynamic model in
yeah,
the pit, what do we use? Alternative 1 or alternative 2?
excuse me?
Usually, what we use for dynamic model for alternative 1 or alternative 2?
You mean alternative 1 or alternative 2?
Yes. So I mean for running data.
Okay, I think the author recommend using distributed lag models. When we do the distributed lag models, we use the OLS methods, right? So in other words, just use distributed lag model.
Okay, bro. Thank you.
Okay.
Okay, bro.
And okay, and I like to mention that we have another class activity due next week. Okay, would you please turn to the page of our textbook, which is on 405, our exercise in chapter 12. Okay, this class activity we'll do next week is on the exercise number 3, 4, and 5. Is that clear to all of you? We'll have number 4 class activity due next week, and that is exercise chapter 12, the exercise number 3, 4, and 5. The 3 questions. In fact, 3 and 4 are related. Okay, and you need to use the data is called mouse 12. The original data is on page 406, table 12.2. And you also can get this data from the data set in the class.
What's the name of data set, Prof?
The data file is mouse 12.
Mouse 12.
For exercise number 3, 4, and 5. And you also need to use this data for question number 5. Is that clear for all of you?
Yes, Prof.
I'll make it as a class assignment. I already did it in our iLearnings,
Okay, Prof.
which is due next week. And so far, this 3 questions is all about the topic covered in 12.1, 12.2, and 12.3, as well as some knowledges about chapter 9. Okay? All right. So that's for this meeting. Okay. Oh,
Prof, mouse 12 data.
pardon?
Yeah, most 12 delta in data set, Colin.
Okay, thank you.
Let me stop recording, okay? And
Okay, Prof.
we'll come back the second session meeting.